So at the end of the last lecture, I sketched the detour that we need to go in order to really calculate the real-time Green's function in k and omega space. And the detour is to go to the imaginary time Green's function or temperature Green's function. And in this Matsubarra frequency representation of this Green's function, we are able to calculate this density, a spectral function or spectral density. And then from the spectral density, we could relay this temperature Green's function to the real-time Green's function. So now the central object of this whole process is the spectral function rho, which we already defined earlier. And there's an important sum rule that we need to check, which is the total spectral weight is actually normalized to 1. So if you integrate over all frequencies for this spectral function, and you will find that this is 1. And this proof is really just 2 lines, very straightforward. We could take advantage of the Fourier transformation, taking you between this gkx and gk omega and gk tau, gkt. So this gkt is actually the inverse Fourier transform of the gk omega by integrating over the omega. But this gkt is actually, again, the Fourier transform of the gkxt, or gk by Fourier integration of a spatial degrees of freedom of the gkxt, you get gkt. But then you could really take advantage of the definition of the g-retarded Green's function, which is nothing but this commutator or anti-commutator between psi and psi dagger. And you know very well from this commutation or anti-commutation relation between boson and fermion operators of this psi dagger, you get a delta function. And then you could really evaluate this Dirac delta function inside this integral over this Fourier integration, and you get 1. So that's from the Fourier integral. But then this 1 is actually the same as that frequency integration over g retarded k omega. And then you could really see this is nothing but this spectral function, because this you could simply just plug in the definition of the g retarded Green's function, k omega, in the spectral representation, which is the omega prime spectral function, right? So you plug in this definition of g retarded back to this Fourier sum for an integral of a frequency, the omega, and you could really derive such a sum rule. So the sum rule follows by simply identifying this normalized value 1 to be the same as this Fourier integral, and you plug in this definition of g retarded, then you get back to this sum rule. Okay, so the sum rule needs to be satisfied because physically we know that the total spectral function should be normalized. And there's a second part of this homework that I assigned to you previously. Remember, this is our previously homework that you need to show by the Cauchy theorem that this Green's function gk omega can be decomposed in terms of the real part, the principal value, 1 over omega, and the imaginary part. So that you could also use the definition of the g retarded and g advanced that we already defined earlier and show that this total Green's function gk omega could be written in terms of the combination of the g retarded and g advanced, but multiplied by a thermal factor in front. So we will use this expression identity later when we work on this specific examples of Green's function in k omega representation. So let's continue. So let me just sketch this and a little continuation.
May I ask a question?
Sure.
When you write that field operator x and t and 0, right? It means it has a special invariant or not?
So which quantity is special invariant?
Because you just write per side 0 and per side x0 and per side.
Right. So in general, you could follow the standard definition. And for translation invariant system, also time translation invariant system, you could shift your t prime x prime to 0, which is often the case.
But even for the spatial translational invariant, it's like a free particle, isn't it?
Yeah, of course, the free particle is example of a special invariant system.
So it's a kind of G0.
Right. In any case, I mean, even if you plug in the most general definition, and this is also true.
But even most definition, I think that the rho is become k and k prime, not only k, right? Because you're only.
Of course, it depends on k and k prime. Maybe k minus k prime.
Maybe this means a special translation.
I haven't checked that, but you can check. But this is true, regardless whether you have a translation invariant or not. This is the most general rule that you need to satisfy, meaning sum rule. So even if we are talking about the translational non-invariant system, this sum rule must be satisfied. So this derivation is just probably the simplest possible way that you can show the sum rule. But of course, I agree that for a translation non-invariant system, you must go back to this original definition. But even in that case, I think you should be able to prove this sum rule. The sum rule must be satisfied, all right? So let me just sketch the detour one more time. This is the complex plane, and G italic represents the Matsubar representation of this imaginary time Green's function. And we could approach the real axis from above or from below. And remember, there are many, many simple poles along the imaginary axis. So if we approach this from above, which means that this I omega and goes to omega plus I eta, and this leads to G retarded. And if you approach this from below, which means that I omega n goes to omega minus I eta, then we could actually reach this G advanced. Therefore, this G retarded and advanced in the real-time representation is nothing but the analytic continuation of this, say, imaginary time Green's function. And then we take this analytic continuation that goes from the imaginary axis to almost the real axis. So this is so-called analytic continuation, assuming that this retarded Green's function is analytic in this upper half plane, so that we could make such a continuation so that the poles of the retarded Green's function is actually slightly below the real axis, whereas the advanced Green's function is actually analytic in the lower half plane, and the poles associated with the G advanced appear slightly above the real axis, so that you could make such a continuation from below. And this is the detour that we should go. So let me just summarize what we can do step by step. The first step is to find G italic as a function of k and the Matsubar frequency, I omega n. And second, from this G italic, we obtain this spectral function, or spectral density. Then we defined this rho is this boundary values. Remember, this identification is precisely this analytic continuation that I just talked about. So the G italic k I omega n, when I omega n goes to omega minus I eta, corresponds to G advanced. And the second term corresponds to G retarded, so you subtract G advanced from G retarded, and you divide everything by I, and this is what we defined earlier, the spectral density, in terms of this capital G. But you don't know this capital G before you can do anything, so then you need to find this out, this italic G. And then you know how to define this spectral function from the G italic, and then you make an analytic continuation going from the G italic to capital G by such an identification, and you could successfully get this spectral function. And also everything you need to know, because then you could simply get this G retarded capital and advanced from G italic. And once you know the spectral function, and you know everything, because the real part of the capital G is related to the imaginary part by this Kronig-Kramers relation, KK relation, remember that. So this is the path that we need to go. Because this is very important steps, so it is necessary to emphasize this one more time. Any questions? So later on we will go through the steps from step 1 to step 2, and then we will get what we want to know. So let's take a short break. When we come back, we will discuss a very simple example, which is the non-interacting particles using such a detour.
Professor, excuse me.
Yeah.
Because the KK relation is quite often appear in the physics, but in general, any complex number, I think real part, imaginary part should be independent. And what kind of condition and the KK relation holds?
Well, the Green's functions are special kinds of function, right? So I agree that this KK relation holds for special kinds of function like Green's function. So it does not hold in general for arbitrary function or complex function. So you could go back to your earlier notes to see why this KK relation holds for the Green's function. So I think the most important part is the spectral function itself. You could see that both real part and imaginary part of the Green's function could be expressed in terms of the spectral density.
If I know the dielectric constant, real part and imaginary part also hold for the KK relation.
Yes, because dielectric function is some kind of Green's function, right? It's the so-called correlator between a number of particles called a density-density correlator. So if you go back to the solid-state physics, so you know that this epsilon dielectric function in K and omega space is related to the density-density correlator. And the density-density correlator is an example of a Green's function. So that's what I meant. So everything that you need to know regarding solid-state physics can be expressed in terms of some kind of Green's function. So if this quantity could be expressed in terms of some Green's function, then this KK relation must hold. So for non-Green's functions, we don't know. You need to show. But if this function can be expressed in terms of some correlation function, the Green's function, then we must have this KK relation. Okay, so you can go back to the solid state one and see other quantities that you are familiar with shows this KK relation. And you will realize that these quantities are another examples of Green's function. So now you appreciate this power of a Green's function. So Green's function is everything. So in one sentence. Thanks for the questions. So let's discuss the very simplest possible example of the Green's function, which is a non-interacting particle. Okay, so remember G italic for non-interacting particles, G italic 0 is nothing but this energy denominator. So this is true for both bosons and fermions. So this I omega n mass bar frequencies could go from even values or odd values. So it's also true. So it is valid for both fermions and bosons. So then we can take this from our starting point and we can define this spectral function. So take this definition that I just wrote down a minute ago. So you could subtract this G italic from the two limiting cases. One is when I omega n goes to omega minus I eta, another is plus I eta, and you subtract one from another, and you divide this whole thing by I, and you get the spectral density. Okay, so this is so simple. This is simply just a Dirac delta function. When omega is epsilon 0 k minus mu divided by h bar, you have a peak, which is certainly the pole position or some kind of a excitation energy. H bar omega is your excitation energy, which is epsilon 0 k minus mu, where mu is the chemical potential. So then from this rho 0 k omega, you immediately get this real-time Green's function. So G0, capital G0 k omega, we could take advantage of your homework problem and write down immediately the full capital G Green's function. So remember, the first term is energy denominator. Here in the first term represents the G retarded, capital G retarded. The second term is for capital G advanced, and there is a thermal factor in front of the G retarded and G advanced, and you sum over these two contributions, you get the full non-interacting Green's function in the real-time domain. Okay, so you could extract this capital G retarded and advanced component from the spectral representation, which is so this is your gamma function. Remember this gamma function as function of z, where z is a complex variable, and when z goes to almost a real value omega plus minus I eta, and you go back to this capital G retarded advanced. Okay, so this is gamma, z goes to omega plus minus I eta. So what is this? Well, this is nothing but you plug in this rho 0, you get. So then this is it. This is the final answer to the non-interacting Green's function at finite temperature. So even though this is a simple example of non-interacting particle, but the non-trivial complication is the thermal factor. It's a finite temperature dependence. So you can see very clearly that by going to the detour, we are able to link between the G italic and capital G by the spectral function. The spectral function is the heart of this identification, and from this spectral representation of a G-tonic and the capital G, you know a thermal factor already. Okay, so the only thing you don't know is the spectral function. So, and this is the only thing you need to know. Because once you know the spectral function, you know everything. Because the spectral, the thermal factor is already there, and from this general derivation of the spectral representation of the Green's function, you know the thermal factor, and this is the only thing you need to know, the spectral density. So we will come back to this for different examples, such as for impurity scattering in the Anderson localization problem, or in this dielectric function, or in this electron-phonon coupling, and in this BCS theory of superconductivity. So let's put this aside and start a new, not new, but the continuation of our earlier discussion regarding the perturbation theory and the Green's function technique. So you can check Feta Logica, this page, for details. And remember, we defined this Green's function in the interacting picture, right? And for a general Hamiltonian that contains both the H0 and interaction. So for a simple case like that, non-interacting particles, you don't have any potential term. But in the realistic solid-state problems, we do have interaction term. And how do we treat this interaction term? And in the Green's function formalism, and we outline and sketch this kind of a unitary transformation interacting picture earlier, but let's just complete the story right now. So remember, we have this G-tonic defined in the x tau coordinates, imaginary time Green's function. And psi and psi dagger are Heisenberg operator, single particle creation destruction operator. And the Heisenberg operator in the imaginary time representation is defined by this transformation, and this transformation is different from the real-time Heisenberg operator, because in the real-time Heisenberg operator, this is unitary transformation with the purely imaginary number appearing in the exponents of this e to the ikt and e to the minus ikt. But here, in the imaginary time axis, this is a real value, this tau. If you take the so-called Hermitian conjugate, you don't get back to the same operator, because if you take this Hermitian conjugate of this psi k xt, goes back to this psi dagger of xt, but here it's not the same thing. So we will come back to this later. So let me just write down the full expression of the k, which is h minus mu n, and h consists of h0 and h1, and h1 is our potential term with the v term. So let's just introduce the S matrix, which is the same as our unitary matrix UI that we introduced earlier. In some textbooks, it is called S matrix, and defined for any tau between 0 and beta. And the definition of this S matrix is as follows. So e to the minus k tau is actually decomposed in terms of e to the minus k0 tau times this S matrix. And this S matrix is nothing but this UI that we defined earlier. And e to the plus k tau is actually S inverse e to the plus k0 tau. So let's take a short break. When we come back, let's just introduce all these field operators in this interaction representation. And then we will derive all these equations that we sketched last time regarding the solution of this unitary operator, S matrix or UI, and so on. Okay, so let's define these field operators in the interaction representation. As we already defined earlier, the single particle operator, psi and psi dagger, in the interaction picture in the imaginary time domain is defined through this definition. So remember, this psi and psi dagger are defined in this fashion separately, where this psi dagger is actually in the interaction picture is defined as this psi dagger in the middle, but on the left and right side of this psi dagger is still this k0 tau e to the minus k0 tau. So you cannot simply just take this dagger of the psi and in this imaginary time representation and you call this psi dagger. So why? Because if you take this dagger of this operator psi, and of course in the middle you get psi dagger, but left and right operators are not the usual e to the I k tau that kind of form, so that this e to the k0 tau, the dagger, is the same as e to the k0 tau. or k0 dagger of tau, but k0 is a Hermitian operator, so this is the same as e to k0 tau. So it's not going to be e to the minus k0 tau, as if this tau is actually I times t. So when tau is I times t, if you take this dagger of this operator, you certainly get e to the minus I k0 t, right? But since tau is a real number, it's a real value, so the dagger of this e to the k0 tau is the same as e to the k0 tau. It's not e to the minus k0 tau. So in such case, we need to define psi dagger independently. We cannot simply just take a dagger of psi, and if you take a dagger of psi x tau, you don't get psi dagger. You'll see the difference. So this is the tricky part of this imaginary time representation of the field operators, because time now becomes imaginary, and the tau is actually real. So any operator involving this e to the k tau is actually a real operator. It's not a complex operator. But still, you can define psi dagger in such a way that it keeps this almost the same form as before when we consider this real-time field operator psi xt. So it keeps the same form as if it doesn't happen anything. But we will come back to this later. But here, just remember that psi dagger is not a dagger of psi. Psi dagger is psi dagger. So let's just compute this equation to get to this S matrix. But before that, let me just make a remark. H0 and n commute with k0. And H0k, H0 tau is actually H0, and N0 tau is actually n. Which means that H0 is a time-independent Hamiltonian, and so is the number particle operator, n is a time-independent quantity. So we can find the solution for S of tau by equation motion method. So let's look at this equation motion for S of tau. So let's take the differentiation of this factor e to the minus k tau respect to tau, and we get minus k e to the minus k tau, right? You simply just take the differentiation of this exponential operator. You get minus k here as a prefactor times the same operator. But what is this e to the minus k tau? So we know very well that this can be decomposed in terms of this e to the minus k0 tau and S matrix, right? So you can show that, let me just define the S matrix one more time. So e to the minus k tau, e to the minus k0 tau, S matrix. So you take the partial differentiation of this e to the minus k tau respect to tau, and you get here, and then you could use this decomposition and also the relation between this k and k0, and also definition of this S matrix, and you can show that this satisfies this equation. So you simply just plug in this partial S partial tau and multiply by e to the minus k0 tau, and then at this term you go back to this equation. So this is a straightforward calculation that you can check. So now you could just move around the right side, left side of part of the equation, and you get partial S partial tau is given by this. So there's a k and there's a k0. So what is k minus k0? So this is nothing but h1. So we just define k. So h1 is your interaction term. So let me just rewrite this in terms of the interaction, s1 of tau times s of tau. And we could solve this partial differential equation of s of tau from this equation plus the boundary condition. The boundary condition is that this s of tau when tau equals 0 should be 1, because at initial time this S matrix does not do anything, so the field operators in the interaction picture is the same as that in the Schrodinger picture. So the Schrodinger operator is the same as the interaction picture, and therefore we request that this of tau equals 0 must be 1. So let's just integrate over this differential equation on both sides over tau and see what happens. So if we integrate this equation, say equation 1 plus the boundary condition, you get s of tau minus s of 0 is given by this integral on the right side of the equation right here. Integration is over a new variable called tau prime. And of course this is not yet done, so again this s of tau or tau prime on the right hand side is still unsolved, and we need to really solve this equation iteratively by this kind of iterative methods that you could get expansion of this s of tau in terms of powers of this h1. But let me just tell you the solution. As I already mentioned previously, that the solution of this S tau is actually the time-ordered exponential operator. So this T tau refers to the time ordering operator. By putting this T tau here, we really ordered all these different times appearing this in the Taylor expansion of this exponential operator right here. So we could do like Taylor expansion of this exponential operator order by order in powers of h1. So we can check this by solving this equation iteratively. So it's a perfect time to take a break. When we come back, we will start to solve this differential or integral equations here iteratively. We could actually go back and forth order by order in powers of h1, and we can show later that when we collect all the terms and sum over all the possible solutions at nth order of h1, and we could actually get to this time order exponential operator. Or vice versa, we could expand this time order exponential, and then order by order we can show that they always satisfy this differential equation. So let's take a maybe 5 minutes break. Let's continue. As I mentioned, let's solve this integral equation iteratively, namely we order by order plug in the previous solutions in the previous order of h1, and we get a new estimation of this S matrix as a function of tau, and we do that iteratively order by order and to get a full solution. So at this cruise level, namely zeroth order, so we consider h1 0, nothing happened, so that this zeroth order solution that S0 of tau is actually its unit, right? Unity. So which means that this S tau minus h0 is actually 0. So assuming that we forget about h1 altogether at the beginning, so we assume that there is no interaction term. Then this S matrix is at S of 0, which means that tau equals 0. S matrix at tau equals 0 is 1, that we already defined earlier. So that zeroth order solution is 1. But we know that this is not the accurate solution because we could forget about this right-hand side of the equation. But we could just build this next order solution based on the previous solutions at previous order. Then we just continue estimating this S at first order in h1 by plugging this zeroth order solution on the right side of the equation over here. So pretending that this S matrix on the right side of this integral is just on the zeroth order solution, and because we know that this is just unit, right? This is just 1, and the first order estimation of this S matrix is just 1, which is at 0. Here, you move to the right side of the equation. This is 1 minus this integral, and this integral is nothing but h1 of tau 1 multiplied by 1, because this 1 comes from this S matrix estimated in the previous order, which is the zeroth order. So you plug the zeroth order on the right side of the equation, you get a new estimation of the S matrix on the left side of the equation. So then we simply just erase this S0 of tau on the right side of this first order solution because this is just 1. So up to here, this is a first order estimation of S matrix up to first order in H1. Of course, this is not the full story because we know that this can be correct. If you plug in this on the right side of the equation integral, here you'll get additional contributions, right? And this is exactly what we should do. So we simply just plug in this S1 solution back to this integral on the right side of the equation, and then we could actually get the second order solutions up to second order in H1 of S matrix. And so this is up to second order, which contains zeroth order in the first order, and the second order is H1. So remember, this double integral here on the second order contributions is not a standard type, but this d tau 1 goes from 0 to tau, but d tau 2 goes from 0 to tau 1, not to tau. Okay, the reason is that if you plug in this integral back to this differential equation, and you could verify that this is the correct integral that you should do. So if you replace this by 0 to tau, d tau 2, then this is not going to work. Because if you take differentiation of the whole thing in respect to tau, and the second integral should be from 0 to tau 1, but not from 0 to tau. If you use that, you don't get back to the differential equation that you start with. So this is a key point, that you get this time-ordered operator. because the second integral t tau 2 ranges from 0 to tau 1, but this tau 1 ranges from 0 to tau, so you get to this kind of a time-ordered fashion between tau 1 and tau 2. So this is double integral over the tau 1 to tau 2, but the integral is down two different directions. One is from this tau 1, where tau 1 represents vertical axis, goes from 0 to tau, but then this tau 2 is actually x-axis, goes from 0 to tau 1, 0 to tau 1, 0 to tau 1. So this diagonal line represents the values of tau 1 is the same as tau 2. And then this integral is down in this kind of a horizontal line, and starting from this bottom of this triangle up to this top of this triangle. So then we'll analyze this later, but let me just go on. So suppose this is just a second order solution, and you can actually plug in this on the right side of this integral, and you get to the third order and fourth order and so on and so forth, and you collect all orders which contribute to this S matrix, and at the end of the day you get this zeroth order, first order, second order, the third order, up to the infinite order in H1. So when we sum over all such different orders in H1, you get to the time-ordered exponential exactly. So this is what we shall prove. But we don't have time to prove all different terms, but we just take the simplest example, which is second-order term, then we show that this is nothing but the time-ordered integral over here, and you divide this double integral by 2, which is a 2 factorial. And inside the integral, you get a non-restricted double integral, which can be done independently, meaning this d tau 1 goes from 0 to tau, same for d tau 2, so there's no such a relation between d tau 1 and d tau 2 in such an unrestricted integral, but the price to pay is that you need to pay attention to the time ordered between h1 tau 1 and h1 tau 2. So let's just prove this identity, and then you could generalize this to any order. So in any order, you simply just multiply the whole thing, independent and integral over tau by factor of 1 over n factorial. And this is precisely this nth order term in the Taylor-like expansion of time order exponential that we just wrote down earlier. So let me just sketch this proof. So you could actually rewrite this integral in terms of the average over two equivalent triangles. Right? This first one is go horizontally like this as before, and the second one is go vertically like this. So the reason why we could actually make such a say identity is because you could actually rotate the square or rectangle. If you rotate this by 90 degrees and you exchange this tau 1 and tau 2, so tau 1 becomes your new tau 2 and tau 2 becomes your new tau 1, and under such a 90-degree rotation and exchange of tau 1, tau 2 variables, because tau 1, tau 2 are dummy variables, it doesn't matter which name I call this tau, right? So tau 1 could be tau 2 and tau 2 could be tau 1. So if you exchange this tau 1, tau 2 and rotate this axis by 90 degrees, you get exactly the same triangle like this, with arrows pointing to the horizontal axis. So this integral is the same as that integral. So you simply just add these two same integral and divide it by 2. You get to this. But the price to pay is that you could, the advantage of doing this is that you could actually combine these two triangles. You get the full square. So if you do so, you can actually, as I mentioned, interchange of the second variable or second triangle. So the first triangle is the same, but the second triangle, you could play some trick since it's the same thing. So it doesn't matter which name I call this tau 1, tau 2. So I simply just exchange tau 1 and tau 2. I get the other triangle, the other half of the triangle, right? So if I add these two triangles together, I get a full square. But remember, there's a factor of 1/2 right here. Okay, so but there's a special properties of the second triangle and also the first triangle is that the first triangle, tau 1, is actually greater than tau 2. because if you follow this horizontal line of this triangle here, and tau 1 is always larger than tau 2. Okay, so tau 1 ranges from 0 to tau 2. So tau 1 is always larger than tau 2. But then the other way around, so the second triangle, you get a different order, which means that this tau 2 is always larger than tau 1. And this is the origin of the time ordered, because we need to add these two terms together, and we need to pay attention to the ordering between tau 1 and tau 2 that appears in this integrand here. Right? So let me just write down this mathematical formula to actually illustrate this diagram here. So the original double integral goes from tau 1 being 0 to tau, and tau 2 from 0 to tau 1, and this is the same as the second term. So the second integral is done by the reverse order, that this tau 2 appears first and tau 1 later, and it is a tau 2 that ranges from 0 to tau, but the tau 1 goes from tau 2 to tau, which is exactly this stuff right here. So tau 2 goes from 0 to tau, but then tau 1 goes to tau 2 to tau. Tau 1 goes from tau 2 to tau. So then we could simply just rewrite this in this time ordered fashion, and plus the second term. So this is, say, 2 prime. So the 2 prime refers to this right triangle right here, where we already interchanged between tau 1 and tau 2, so that this tau 2 is always larger than tau 1. So the first term is still the first term, but the second term is actually converted into this another time ordered fashion, that this tau 2 is actually larger than tau 1, and we switch the order between tau 1 and tau 2 right here. Yeah, because these two integrals are identical. So then we could simply just combine these two. So now we have the symmetry, right, between this first and the second term, because now this d tau 1 goes from 0 to tau, and d tau 2, the first term goes from 0 to tau 1, but the second term from tau 1 to tau, so you can actually combine these two. And by using the theta function, which takes care of the order of tau 1 to tau 2, so I put the theta function in front of this first and the second term to guarantee that this goes back to the previous step, because the first term survives only when tau 1 is larger than tau 2. This is precisely the condition that the first term survives, right? But when tau 1 is less than tau 2, the first term vanishes, which is also the case when tau 1 is less than tau 2. We don't have this first term. So, and similarly for the second term, which survives only when tau 2 is larger than tau 1, which is precisely this 2 prime diagram shows. And indeed, when tau 1 is larger than tau 2, the second term vanishes. And what is this? Well, this is nothing but the time-ordered operator of this product between h1 tau 1 and h1 tau 2. So this is the definition of the time-ordered operator. So by definition, when I put this time-ordered operator in front of this product of these two operators, h1 tau 1, h1 tau 2, what I mean is that when tau 1 is larger than tau 2, this order is the same, h1 tau 1 times h1 tau 2. But if tau 1 is less than tau 2, I need to switch the order. But the h1 is also the h1, no matter which time that this h1 is evaluated. So I need to switch the order between h1 tau 1 and h1 tau 2 if tau 1 is less than tau 2, or tau 2 is larger than tau 1, and which is exactly what I wrote here. When tau 2 is larger than tau 1, so the proper order is that I should write h1 tau 2 first on the left of this h1 tau 1. And this is the definition of the time-ordered operator. Remember that. So any time-ordered operator should actually follow the same definition. So then we already proved that the second-order term is actually the time-ordered product between this h1 at different times, tau 1, tau 2, and the integral is unrestricted, which ranges from 0 to tau for both tau 1 and tau 2. But then the price to pay is that we have to put the factor of 1 over 2 factorial, and then we should order the h1 operator. So this derivation holds for arbitrary order. So you can show that this is also the case for the third order term. The only thing that you need to change is that you need to change the 2 factorial to 3 factorial in the denominator, and this time ordered operator is actually among 3 h1s at different time, tau 1, tau 2, and tau 3, and so on and so forth. You can generalize this to any order. So let me just write it, the full solution right here, so we could easily generalize it to nth order in this iterative process, and the final solution for S tau is nothing but time ordered exponential, and by definition, this is nothing but the time ordered operator of this Taylor expansion from 0th order to infinite order terms, where you have this constraint, all this tau should follow this order. So tau 1 should be larger than tau 2, and tau 2 should be larger than tau 3, and so on and so forth, up to nth order of time, tau n. So if you sum over all such nth order terms, and you define this as a time order exponential operator. So this is the formal definition of the time order exponential operator, which is nothing but the time ordered, the sum of all nth order time ordered operators. So 0th order is just your 1, and the first order is just a single d tau integral over h1, and the second integral, as we just showed here, is just 1 over 2 factorial, this time order h1 at different time, tau 1, tau 2, where you need to make sure that tau 1 is actually larger than tau 2, and so on and so forth.
Excuse me. In general, we have a time order operator. I think we will swap need to depend on the boson or fermion. Here we didn't have the positive and negative side due to the Hamilton always projective of the field operator.
Of course, H1 we didn't talk about whether this boson or fermion operators are there for H1, but we will get there when we talk about specific examples of H1. But in general, this is true for both fermionic and bosonic representation of H1. So you can see that we don't need to specify whether this H1 contains the bosonic or fermionic operator at this level. So the key point is these 2 different time orders when we write the same H1 at different times, but we need to take care of their order. So that's all we need at this point. It doesn't matter what H1 is. So we complete the circle that I promised to prove a few lecture hours ago. So then you should be confident and comfortable about this time-ordered exponential operator as a solution for the the S matrix in the interaction picture. So we will take advantage of such solutions for later discussions when we do this perturbed expansion and evaluate the Green's functions, including the H1. So far, we cannot deal with the system with interactions. So this is a highly technical problem because first thing, the finite temperature Green's function is complicated enough, and then the Hamiltonian will mess up our calculation because the interaction term. So the interaction plus the finite temperature Green's function. So it is a really tricky calculation. But fortunately, we have an approach that works. Okay, so let's take a short break. When we come back, let's just go back to this Green's function in the interaction picture that I introduced earlier. So as I mentioned previously, that we will go back to this point, and then we showed that this will help us. This is the only way that we could do something at the finite temperature and in the presence of interactions.
In the real time, we also have a similar result, right? For the interaction picture, for the unitary.
Yes.
But why we cannot use that result, just replace t by the minus I tau? I think we'll get the same result, right?
Yes, you're right. So in the real-time representation, there's a unitary operator, ui, remember, we introduced earlier, and the proof is actually the same, follows the same derivation that I showed here, right? So except that this tau is replaced by it. So yeah, you are right. So we could simply just use our earlier, so the real-time time evolution operator in the interaction picture and replace t by I tau or tau by it. Yes, we can do that. But here, since we know that we need to take a detour So we should do it everything in the imaginary time axis anyway. So let's just look at this property, nice properties of this S matrix. And we can define this S matrix, which is some kind of a time evolution operator, taking you from these two different times from this tau 1 to tau 2. And we define this as S of tau 1 and tau 2. So the previously single time S matrix is simply just as tau 0. So when we set one of the tau, say tau 1 or tau 2 be 0, and this is just what we just defined. But we can generalize this definition of a S matrix to depend on these two different time. And we need that because there is a nice properties of S matrix, and you can show that for three different times, tau 1, tau 2, and tau 3, they follow this order. And if you multiply this S of tau 1, tau 2, and S of tau 2, tau 3, and at the end of the day, this tau 2 disappears, and you find that this product of these two S matrices is nothing but S tau 1, tau 3. Okay, so this property is the same for this S matrix in real-time evolution, and you could define this S of tau 1, tau 2 as a product of these two S matrix, S tau 0 and S tau 2, 0 inverse. So we already defined this S inverse operator, and then you could pretty much show that these relations hold. From these two relations, we could show that this two-time S matrix S tau 1, tau 2 is given by this one-time S matrix tau 1 times S inverse of tau 2. The reason why we should actually multiply this S inverse of tau 2, not S tau 2, is because this tau 1, tau 2 appears at different upper and lower limits in this time integration. So this tau 1, tau 2 plays this upper and lower bound of the tau integral. As a result, the other one should be inverse of S. So we will take advantage of such relation later. So let's just go back to the Green's function in the interaction picture. As we already defined earlier, that the Heisenberg operator defined in imaginary time could be written in terms of the operator in the interaction picture, like this. So psi k0 x tau refers to this destruction operator in the interaction picture. Remember that. So if I remember correctly, this is S. When you time evolve the Schrödinger operator from tau equals 0 to tau equals tau, you go to this operator in the interaction picture. And so these are just definitions that we are already defined earlier. So then we will take advantage of such nice properties of this S matrix, which we will need to simplify this finite temperature Green's function in the presence of interactions, because the product among the three S matrices, S beta tau 1, S tau 1, tau 2, and S tau 2, 0, is actually S beta of 0, which is S of beta. You can actually use this relation right here for this, the product among three S matrices. So all the intermediate degrees of freedom disappeared after you multiply all these three operators together. So only the initial and final time survive. So we will take advantage of such identity when we simplify this Green's function. So remember, previously we defined this G italic at imaginary time domain. So when tau is positive, we have this time-ordered operator, and S2. Okay. So I think this is okay. This is the correct definition of this destruction operator going from this interaction picture to the Schrödinger picture. So let's just take advantage of such nice properties of this S matrix. The definition of this italic Green's function when tau is positive at finite temperature is actually this partition function, this e to the minus beta omega appearing in the denominator, and time-ordered operator of all this product of this Heisenberg operator. So we could rewrite this Heisenberg operator in terms of an interaction operator, and this thermal weighting factor, the Boltzmann weight e to the minus beta k, can be represented in terms of the product of e to the minus beta k0 times S of beta that we already showed previously. And the first group of this operator is psi of x1 and tau 1 in the Heisenberg picture. Remember that. And the second group is actually psi dagger in the Heisenberg operator x2 tau 2. So let me just assign this to you as a homework exercise. Prove it. So following the standard definition that we already defined earlier, that you could transform your Heisenberg operator either to the Schrödinger operator or to the interaction picture operator, right? So, and then use these nice properties of the S matrices, and you can show that this Green's function in the interaction representation of the operator is this form right here. But then we start from here, we could further simplify this into the minus beta 0 S of beta tau 1 psi of x tau 1 S tau 1 2 dagger of x2 tau 2 S of tau 2. So you could simplify all these S matrices by actually moving around all these S matrices inside the trace, because trace ABC is a trace BCA, is trace CAB, and so on and so forth, and you use that properties and you move around all these S matrices and you combine all these different S matrices, and then you could actually use that nice properties written here when you multiply the three S matrices with this connected time inside the argument, and we could actually simplify this product and write it as a single S matrix right here. And that's how you get this S beta of tau 1 and also S of tau 2 right here, because all the remaining S matrices are gone by using this property right there. And similarly, we could show that this for G italic tau negative, we get S of beta tau 2 psi dagger x2 tau 2 and S of tau 2 tau 1 psi of x1 tau 1 S of tau 1. So we can derive this G italic in an imaginary time representation for both tau positive and tau negative, and this derivation for tau negative follows exactly the same path, except now we should take care of this plus minus sign in front, and all these S matrices look very much the same, except now we should really pay attention to this tau order between tau 1 and tau 2. Since when tau is negative, then we should switch the order between tau 1 and tau 2 right there, and also switch the order between psi and psi dagger so that the psi dagger appears to the left of the psi, and you switch all this around between tau 1 and tau 2, and you go to this negative tau G italic. So together we have this, again, time-ordered operator. So you could show further that the three S matrices can actually be combined and converted into the single S matrix, which is S of beta, because when you move around those S matrices, then you could use the nice properties of this, the product of three different S matrices, say S beta tau 2 and S of tau 2 tau 1 and S of tau 1 0. So then all this tau 2 and tau 1 and the S matrices in the middle are gone, and then you end up getting just S beta of 0, which is the same as S of beta.
Here we need to cyclic movement, or can you actually move?
Yeah, this is what you can show. You could actually move around all this psi and psi dagger so that you could intentionally move all these S matrices together.
No need of cyclic. The ABC, you cannot become a BAC.
Right, but you could really show, right.
The two field operator, the S equal, you have a constraint for cyclic. It's very difficult to become the less form. Or you can arbitrary, because now you prove like you arbitrary, you can arbitrary interchange.
Right. Okay, I guess time is up, right? Exactly. Okay, so yeah, we end our lecture today here. So let me summarize. So we showed this non-interacting Green's functions at finite temperatures by using this detour approach that we first evaluate G italic and spectral function, and then we can get everything we need to know. And then we go back to this interaction representation of this Green's function and imaginary time representation, and we prove this time-ordered exponential as a solution for this S matrices, and then we take advantage of that nice properties of S matrices, and we simplify this G-italic Green's functions, and we finally derive this simple form. So next time we will start from here, and you know that this S matrix depends only on this interaction H1, and there's only a single S matrix remain here, okay? So that we successfully combine the thermal weighting factor and the time evolution in measuring time axis, so which allows us to do perturbation. So next step is to do perturbation starting from this G-italic right there, and then we could introduce all sorts of techniques that establish in the literature, such as Feynman diagram, weak contraction theory, and so on and so forth. So enjoy this Green's function. I'll see you after spring break.